Good afternoon, students. This is EE 330. We're still continued on chapter 1. This is week number 3. Considering the first week is not no lecture, so we started from the second week. Consider it that as of the first week. Okay, we're continuing on P-N junction in equilibrium. So I think it's not clear. Okay, let's continue with this. So let's say we have, this is the PN junction. So most likely we have all positive charge on this side, negative charges on this side. And let's say we have also negative charge in the PN junction. And on positive charge here. And we're gonna look at the electric field. So this is PN junction. The electric field is going this way. So I will consider this is the electric field distribution due to the, this is the p-type and this is the n-type. So because this area is highly doped with Holz concentration, so most likely up to this point, I put it, so it should be a constant on this level, the electric field. Due to this region have the negative charge, which is from the n-type, the electric field will go down. So most likely here we have the dE due to dx is equal to 0. So because of the negative charge, it will go down. To the n-type. Also in this region we have another constant dE dx is equal to 0. This is the energy band. And at this region here, because the electric charge due to x is going down, so it is different than 0. So dE dx does not equal the 0 at this time, because at this time it's decreasing because it's going from the p-type to the n-type, but there's like a highly doped a p-n junction on the p-type with electrons or negative charge, and on the n-type there's positive charges. So this is the number or the doping concentration on the p-type. This is N8. That's the distance from the energy band from the reference point. And also on this side, this is the doping concentration on the n-type and D. So if we continue further to do the depletion consideration, I'm just going to continue from this. Let's put this is X, and this is the volume rho V, the volume charge density. Volume charge density, that's rho V. So to identify the potential in the p-type, there is no charge in this. There's no charge in this field. So most likely this is 0. So we can consider it as neutral because it's purely doped with holes. I'm gonna put it down in blue. So when we reach to this area, where we're gonna, this is, we can say this is completely ionized region. So we can consider this as neutral. So when we reach to this side on the p-type, there's negative charges, so there's something going on. So this area is the presence of the negative charges in the p-type. So it will go down in this manner, and at a certain point gets constant and will be close to 0. At this minimum point here, it's the negative charge with the doping concentration on the p-type, Na. So on this side, that's the n-type. So it's most likely will be number of holes on this type, on this region is high. So this is completely ionized region in the n-type. It's constant here. So also we can call it neutral. And then after that, the negative charge will kick in and it will go down to 0. So most likely, sorry, this is the neutral side. This is the completely ionized region. And let me erase this here. This is completely ionized region. So most likely this region in the positive, due to the positive in the n-type, it should be by theory the same size as this, the negative type that presents, because before any interaction between the positive and negative, the number of charges should be in balance. So at this time, so here where the in this region here, we can call it partially ionized. Also in this side here, this is the partially ionized region. Okay, so to do a depletion approximation, I'm going to use a red line. We're not going to consider any partial ionization. So most likely neutral in right away will go down to very straight line that will go down to completely ionized, 0, and then goes completely ionized to neutral. So this is the depletion approximation. Depletion approximation. So also this is Q and D, the charge multiplied with the doping concentration on the anti. So as I said, this region should be equal to the same as this region. So most likely this is XP and this is XN. So if we QND XN is equal to QNA XP. So the charges will go, we end up with ND XN is equal to XP and A. So if we look at the, we still continue here. So this is the electric charge due to X. So I'm just going to put it down like this. So there is no electric charge on this side here. And this is the electric charge will be negative. And then on this side will go up. And then 0, almost 0. Here, we can't say that this is, since this is neutral, we can't say that this is exactly 0. We can say that x of p is really small because the doping concentration on the p side is much higher. There is no reaction with the negative. So because Na on the p type or side is higher, we can say the same thing on this side. So this is almost close to 0. That's as in terms of the electric field. Okay. So to continue, the drift current density. We already know that on the p-n junction equilibrium, where the drift current density on the p side and on the n side, also the density for the diffusion, this is the drift, plus the diffusion, DIFF is the diffusion, is equal to 0. In this term, we have Q px mu p ex dp dpx divided by dx. It should be equal to 0. And on the n-type or n-side, the current drift density with the current drift or diffusion density on the n-type also is equal to 0. That means Q and X mu n Ex plus Q dn dnx dx is equal to 0. So when the electric field is 0, aptly called the neutral regions. This is page 1, page 2. So to continue here, on the P side, the total charge, which is Q negative, is equal to minus Q and A multiplied with the area XP 0. And on the N side, total charges is Q positive equal to Q and D area XN 0. That means Q positive is equal to Q negative. So we proved here that the electric charges on this region should be equal to this region. So that means negative Q and A XP0 is equal to Q and D XN0. That means XP0 XN0 is equal to ND divided by NA. So considering that the rate of electric charge due to the distance from here to here, from here to here, so all of these rates are taken into consideration by dE dx is equal to, this is the charge density due to the distance, epsilon for the silicon, Si. So knowing that the E is the direction of the negative X. And this is the charge density. And this is epsilon. Silicon's permittivity is equal to 1.04 picofarad per centimeter. So right portion of the SCL. So we have dE dx is equal to E m0 divided by xn, and rho divided by silicon epsilon is equal to QND divided by the way, this is written like reversed E for the silicon. So EMO divided by XNO is equal to QND divided by epsilon SI. So the final EMO is equal to QNA XPO divided by epsilon for the silicon equal to QND. This is on the N-type, X and O So let's solve one of the problems from the book. So most likely, we're gonna solve 128 from the book. Page 3. Problem 1.28, and that's page, let's see, 97. So I'm going to read it. To develop a feel for the conductive properties of different materials available in IC technology, let us estimate the resistance R of a bar of the type of figure 1.36a. Well, I'll put the right now. Sorry. So if it is 10 micrometer long, 1 micrometer thick, and 2 micrometer width, so every 1 micrometer is 10 to the power negative 4 centimeter, and is made up of the following material. First, we're going to consider it as pure. A is pure silicon. So let me put the figure 1.36a. So this is what figure 1.36a. So we are using, in the beginning, the pure silicon material. So pure silicon material, first of all, we need to account for the resistance. So they're asking for R when it's pure silicon. We know from the given the length, it's 10 micrometer. The depth is 1 micrometer, and the width, it's 2 micrometer. So most likely the formula we're going to use is R is equal to E length divided by the area. So we have the length, which is 10 micro times 10 to the negative 4, which is in centimeters, divided by the area is the length multiplied with the width. So most likely 1 times, or the depth, 1 10 negative 4 multiplied with 2 times 10 to the negative 4. So we end up with, and multiplied with E. So R is equal to, oh, we can do this one. So it's 10 negative negative. Okay, so it's 5 times 10 to the positive 4, E. Now we need to account for E. So E is equal to 1 divided by charge, and I for the silicon, mu for the P side, and for the N-type side. And we have all of these givens. 1 divided by the charge is 1.6. That's constant, negative 19. Also, the Ni is 1.4 times 10 to the power 10. Then mu is 45 plus 427 plus 68 plus 1, 346. So most likely E is equal to 2.4 times 10 to the power 5 ohm centimeter. So we substitute everything for R. 5 times 10 to the power 4, 2.4 times 10 to the 5, which is 5 to the power 4 times 2.4 to the power 5. So it's 1.2 times 10 to the power 10 ohm. So I just want to share with you, probably some of you is asking, where did I get this formula? So in the problem, they're asking to use the equation for R, and that's from Back to Physics. That's the hint. Okay, built-in potential. The built-in potential, which is phi 0 So the electric field always accompanied with electric potential. Gradient. So we know that electric field is equal to the negative dq dx. If we solve for phi, we're gonna integrate e dx. So let me explain to you inside what happens. So this is p-n junction. So this is and we have the negative. So most likely on the p-type, so there is no built-up potential. So on this side, there is no potential built up here. This is Vp. And after a certain period of time, which is negative xp, the potential start built up to the point where this is what we call here the built-in potential energy. So most likely this is phi 0. So most likely is equal to 1/2 xp xn multiplied with q and d xn divided by epsilon. So this is what we are integrating this area. As for the energy band, so because of the positive here, there's initial, so energy, let's see here, and it's gonna go down up to the point where it's gonna be neutral energy. This is the energy band. Neutral. Energy. And this is VT. We're gonna talk about it. So to continue the integration, so So the built-in equilibrium potential is phi 0 is equal to the potential on the n-type minus the potential on the p-type. Equal Vt dpx is equal to negative Vt dnx and x. So using phi x is equal to negative from x p0 to x n0. So most likely this is x p0 and here's going to be x n0. Is equal to ex dx. Integration from qf to qe. Not q is phi. Is equal to negative Vt ppo pno dpx divided by px is equal to Vt and p0 and n0 dn x and x, it's on the n-type. So in this case, x is equal to negative xpo and x is equal to positive xno. In this case, phi 0 is equal to phi n minus phi p. We substitute both values, Vt, ln, ppo, pno, we can also write phi 0 is equal to Vt ln Na Nd divided by Ni squared. For the n-type, is Vt ln Nd Ni, and for the p-type, same thing, is equal to Vt ln Ni divided by Na. Okay, now the electric field which is the EMO, and so now we wish to drive the expression for all of the other junction parameters in the PN equilibrium. So this is the maximum electric field strength. So usually we found it by the integration of the charge due to the X. And also the SCL width x do. I think this is already passed. I did not declare what is it. This is the space charge layer, and also the SCL for the charge Q J0. So it's Q, we can write it Q J0, so it doesn't matter. So in this form, the maximum field strength EMO, so we have phi0 is equal to xp0 xn0 multiplied with EM0, and we're going to consider this is our equation number 1. And also we have xp0 xpo. XPO is where the energy, the electric energy profile is the point where we reach from 0 all the way, start going up into building the potential built in. So this is the point where it leaves the x-axis from 0 to higher than 0. That's the point where the increase of the energy band due to the charge built up. Okay, so is equal to epsilon for the silicon divided by QNA multiplied with EMO. So we're going to consider this is our equation number 2. And also this is for the N-type, same thing. We're dealing with silicon. Q ND is the concentration on the N-type multiplied with EMO. That's going to be our equation number 3. We're going to substitute equation 1 and solve for EMO. So we're going to substitute XP and XNO in equation number 1. So we have this and this. We're going to substitute it here, and we're going to end up with square root of 2q phi 0 divided by epsilon multiplied with NA, ND, NA plus ND. And we're going to consider this as equation number 4. We're going to substitute equation 4 in equation number 2. And we can do that in equation number 3 also. P is equal to square root of 2 epsilon for the silicon, 0 divided by Q and D, NA plus ND. And this is going to be equation number 5. If we substitute equation number 4 in equation number 3, we're going to end up with the same thing. Two epsilon Q and this is NA, this is ND, And this is what I'm thinking. This is so most likely this is an A, this is ND, this is ND, NA, equation number 6. So most likely the sum for XP and XN the sum of equation 5 and 6 will give us the space charge layer for the XD0. Skipping math to epsilon for the silicon, 1 over NA plus 1 over ND. And we're going to consider this is number 7. So now J0, the equilibrium charge, this is J0 or JO, which is also a Q positive, is equal to Q ND multiplied with the area X and O. So we're going to substitute equation 6 and QJO is equal to area outside 2 epsilon for the silicon, Q phi 0, and A and D, and A plus ND. So we're still continuing. So on the P side, the voltage, usually the positive, the voltage is greater than 0. So most likely, which is bring the forward bias. And for the N side, the voltage is less than 0. So most likely that's the reverse bias. So for the maximum electrical or electric field or electrical field, strength as a function of voltage. So EMV is equal to 2Q VO minus V divided by epsilon for the silicon, and A and D and A plus ND. So most likely we're gonna extract the equation for the EMO for this from this equation. So in this term, we have square root of 2Q, same thing, divided by epsilon SI, and A and D, and A plus ND. And that will be multiplied with square root of 1 minus V divided by phi 0. This term here, or this is EMO. So we can write EMV as EMO square root of 1 minus V divided by Q0. Whole thing is under. Then XD V is equal to XD0 1 minus V divided by Q0. Also, it follows QJV is equal to QJ0 square root 1 minus V divided by Q0. So XD0 and QJ0, those are zero biased component, which is when the voltage is equal to 0. So let's solve a problem from the book. 133, it deals with the p-n junction equilibrium. So let's solve problem 1.33 on page, what page? Page 198. It's only 98, sorry. So let me share the screen with you. Okay, so sketch and label the charge density rho x, the electric field Ex, and the electrostatic potential phi x for a p-n junction of the type of figure 1.38 or 39 if the p side doping is kept fixed as Na. So we have Na is equal to 10 to the power 16 per centimeters cube, but the N side doping is progressively increased as follows. So we have Nd is equal to 10 to the power 16 per centimeters cube, symmetric doping. Same thing, symmetrical on the other side. So in order to do this, we have to find rho, QM, and EMO. So usually, let me write the formulas. So or we need the, let me stop sharing. So EMO is equal to, we already took this formula. I still remember it. 2Q phi 0 divided by epsilon for the silicon NA, ND, we already have this one, NA plus ND. So in this term, we need Q0. So Q0 is equal to Phi n plus 0.35 volts. We need Q Phi n. Phi n is equal to 26 millivolts. Ln and D we already have 1.4 times 10 to the power 10. So we can solve for this. And Qn will be equal to 0. Considering that this is 10 to the power 16, 0.35. Okay, in this term we can calculate for Q0. It will be 0.35, okay, 0.70, 70 volts. So we have Q0. Now we can get the EM. We have the value for this as constant. So most likely we end up with 33 kilovolts per centimeter. And also, we need to get the value for EX, rho X, QX. Okay. So we need the value for phi p is equal to 26 ln 1.4 times 10 to the power 10 divided by 10 to the power 16. And this will be equal to negative 350 millivolts. So all of these values and for so we got XP, I mean phi p. So we need to xn0. We need xp0 and xn0. And the formula for these, xp0 is equal to square root of 2 epsilon phi 0 divided by Q and A multiplied with ND, NA plus ND. And for X and 0, it's the same thing, but 2 epsilon silicon phi 0 Q and D and A plus ND. So we have all the components for this. We have Q0, Q, and D, and A. So we do the substitution. We should end up with both should be the same because ND and NA are the same. 213 nanometer. So we got X and 0, XP0, phi P, phi N, phi 0, EM0, oh, the rho P and rho N, rho P and rho N. What's the values on rho P and rho N? We need to use the formula. So rho P will be equal to an I square because we're using an A, and this is an I square and D. And this will be equal to negative 1.6, 1.6. And this is going to be in meter column centimeters cube, meter column centimeters cube. Okay, let's see the representation for the plot. This is to continue problem 1.33. I'm going to keep this value here. So if we're doing the, I'm going to do one of them because let me share the screen. Part B, it's going to be the same thing, but instead of using ND, the same as NA, ND will be changed into 4 that amount. And you're going to see how it's going to change. And in part C, it's going to be 10 to the power 17. So I will leave those for you to do since it's going to be almost the same as part A. So this is X. This is rho. Also, I'm going to do just one value, X. This is Q. And also, this is for the EM0. So for rho, so we have negative 1.6 and 1.6. So we have, let's say this is 1, negative 1.6, and 1, 1.6, 1.6. So on this side here, so we have XP. So most likely, on this side, we will have XP0, and in this side, we have XN0. So the value for XP0 and XN0 are the same, 213. Let's say this is 100, 213, 100, 213. So negative 213, 213. So most likely, this is for the rho. Here at this point, this is rho N, rho P. And we are getting the values from the first one. We have ND is equal 10 to the power 16. For the Q, so most likely 213 is here, and negative 213 is here. So the shifting point is so we have it's most likely negative. Here it's going to be negative 350, and here's going to be almost the same 350 or 0. Sorry, 0.35, and this is 0. Let's say here 0.35, 0.35. So it's going to be when the positive is on the p side, and it's going to go up to the n type. And for the EM0, the value is 33. So we're still continuing from, because all of these points are fixed, XP0 and XN0. This is going to be in the middle, so let me erase it. So it's going to be continuing in this format. And negative 33. Charge going like this, going down due to the negative in the positive, and this going up due to the positive in the negative, and then so usually this is what we call a completely ionized region. Ionized region, and also this is completely ionized. This is neutral, and this is neutral. There's no, we're not talking about the partially ionized region. Okay, let's continue each. Capacitance. So usually when we apply voltage across the PN junction, this is the P type, this is the N type. So usually there is a charge concentration when the electron is jumping over the PN junction, and the holes will go over. So it will create like capacitance or capacitive behavior. So due to the redistributive of the SCL charge, so it is called CJ, which is the junction capacitor. So as for this, or we can say is the ability or ability to store charges due to the PN junction potential. And we already know that the capacitance is the total charge divided by the voltage. In this case, Cj is equal to dQj, which is the small signal, capacitance, dV. It will change due to the voltage. So we have Qj as a function of V, we're already Qj0 square root 1 minus V divided by phi 0. So this is already proved. So we're going to apply differentiating the QJV, apply differentiating QJV. So we end up with CJV is equal to CJ0 divided by 1 minus B, and this is to this square root of M, or to the power M, which is the grading coefficient. So usually M is the grading coefficient. So usually M is equal most of the time half or 1/3. So most likely. And CJ0 is equal to the area epsilon SI charge divided by 2 and A and D and A plus MD. This is junction capacitor. So we'll stop here for this week. Sorry, and we will continue on chapter number 1 next week. Thank you.